If you've ever watched someone solve projectile problems like it's nothing, here's what they're actually seeing. So how it's going to work is I'll solve a problem and then I'll give you a similar example to solve on your own, and then we'll escalate in difficulty. So the first problem for today is a ball is launched horizontally at 12 meters per second from a cliff that is 20 meters high. And the question is asking us, how far from the base of the cliff does it land? So what that means is if the ball follows a path that looks like this, then we have to find the distance from here to where it landed. This is called the horizontal range. And horizontal range, we can label as x. That's what we're looking for. Let's list out what we know so that we can work toward finding x. First, we have the horizontal component of velocity, which is 12. We also have the height of the cliff, which we can label as y. And this matters because the height of the cliff affects the air time, which affects how far it's going to land. And that's what we're explicitly given. But we always know that on Earth, gravity is roughly 9.8. That's our acceleration. And finally, x is unknown. And also, time is unknown. That's important because the horizontal component of velocity multiplied by the time you're in the air. We have the horizontal component of velocity. It's 12 meters per second. But how about time? That's all we need to solve for. So what we've done is we've labeled what we need, what we have, and what we're missing to get what we want. To find time, we have to find a formula that involves t with every other variable as a known value, because then we simply just have to solve it. The formula we can use looks like this. Y equals initial vertical velocity time minus 1/2 gravity time squared. This looks a little bit complicated, but don't panic. If you notice, initial vertical velocity is 0 because there is none. It's a horizontal launch. So this term cancels out. It's nothing. The rest is pretty simple. So the actual formula that we're going to be using is y equals 1/2 gravity times squared. I didn't include the negative sign because it doesn't really matter in the final calculation. We're solving for a time value, which is going to be measured in seconds. You don't have negative seconds. So that's our formula. And if you rearrange for t, you get this. T equals root 2 times y over g. You can go through the rearranging steps yourself, but this is the formula that you get. And if you're a little bit lost on why I chose this formula, it's because 1, it contains time, which is what we want. And 2, every other value in the formula, so gravity and y, we have is listed. And that's what you should base your formula selection on. Anyway, plugging in values into this formula, so 2 times y, which is 20, divided by g, which is gravity, 9.8. The time it takes to hit the ground is roughly 2.02 seconds. And now, with this time value, we can plug it in right here to find the horizontal distance covered by our ball. Let's do that. X is equal to Vx, which is 12, multiplied by t, which we just found. We get roughly 24.2 meters. So once our ball hits the ground, it is 24.2 meters away from the base of the cliff. I'll give you the chance to quickly pause the video and try this problem on your own. It's a similar method, and in a few seconds, I'll solve it. So the solution to this one is the same thing. Your rock is thrown horizontally 15 meters per second off of a platform 45 meters high. We have to find the range. The range formula, which is the same as x, by the way, but this time I'm writing it as r. It's equal to horizontal speed multiplied by the air time, which we again don't know, but we can use the same formula. T equals 2y over g. Let's sub in our values. So 2y is 2 times 45. Gravity is 9.8. This gives us roughly 3.03 seconds. Let's plug this in here, and we get roughly 45.5 meters. This is the third problem. A soccer ball is kicked at 20 meters per second at 30 degrees above the horizontal. So when you see the words above the horizontal, what that means is take a look at the horizontal and you just go up and up and up until you're at 30 degrees. This helps you know which sides the angle is in between if you really need to get specific. And we're asked, how far does it travel before it hits the ground? Which is, again, horizontal range. However, it's a little bit different because it's a symmetrical launch. We start on a certain y level and then we end on the same y level. With angled launches, it's always useful to start, no matter the question, with breaking down your vector into its components. This is because the initial velocity vector's components, that's what's used in the formulas. It's rarely the actual velocity vector itself, which in this case is 20 meters per second. To break it down into its x and y movements, for x, you get the vector 20 and you multiply it by cosine of the angle. And for the y component, you do the same thing, but you use sine. The x component and y component are 17.32 meters per second and 10 meters per second, respectively. Now let's look at the question again. So we're looking for horizontal range. x or r, whatever you want to label it. And x is found with the horizontal component of velocity multiplied by the air time. We have the horizontal component, which is here, 17.32. We just need the air time. And the time of flight is found with this specific formula. 2 times velocity, specifically the y component, divided by gravity. That's 2 times 10, taken from here, over 9.8. That gives you a number of roughly 2.04 seconds. If you go and plug this in for time, then you find that your horizontal distance covered from the soccer ball, roughly 35.3 meters. So the big picture idea for angled launches, break it down into its components and then solve like normal. And if this is helping you see the problems more clearly, or if you're wondering how some people can break these problems down in the mind like this on instinct, that's the whole point of the physics fluency challenge. It makes it into a repeatable structure that anybody can use. The link is below if you want to check it out. I'll give you a second to pause the video and try this problem on your own before I give you the answer. And now I'll solve this problem. So again, before we do anything with angled launches, which this one is, I prefer to break down the vectors components before solving any problems. So the x component is 18 cosine 45. And the y component is 18 sine 45, giving us 12.7 meters per second for both of them because cosine and sine 45 are equal. We're looking for the horizontal range, which again is the same problem. We have the x component of the initial launch velocity, but we don't know the time of flight. So the time of flight can be found with this formula. We used this in the previous problem. T equals 2 and the y component of velocity divided by gravity. That is 2 times 12.7 over 9.8, which is roughly 2.59 seconds. So that's the flight time. All we did was plug the numbers into the formula. And then we plug this into the range formula, giving us roughly 32.9 meters for our basketball. This is the second last problem, and it's going to be a little bit trickier. So a projectile is launched at 25 meters per second. That's the initial velocity. What angle gives us the maximum horizontal range? So if we launch something, what angle do we launch at to cover the most distance? And what is the value of that maximum range? We're tasked with two things, the angle and the actual distance. So we're going to have to take a bit of a unique approach here. Instead of the standard range equation, which is velocity times time, we're going to be looking at the alternative variant, which is velocity squared sine 2 angle divided by gravity. And what's special about this is it involves the angle. The angle actually controls the horizontal range. And for the maximum horizontal range, you would want this value here to be as big as possible, right? Or as close to 1 as possible. And sine 90 degrees is equal to 1. So that means sine 2 multiplied by whatever our angle is, which is 45 degrees, would be equal to 1. Which means that for the maximum horizontal range, the angle that we should launch our thing at is 45 degrees. Because that's what the formula tells us. This is not really a formula plug and chug problem. It's also not something that you can just do with simple reasoning and basic problem solving skills. This is a fluency and deep knowledge problem. It comes from being able to derive the formulas and having solved enough of these problems on your own with the methods and the right approaches. So if you didn't see this one immediately, that's expected. If you did, that's impressive. So that's the first thing. 45 degrees is the best angle to launch our projectile. What about the distance covered when we launch it at the optimal angle 45? We can find this with this formula right here. So let's plug in our values. Range equals velocity squared over gravity. We're going to ignore this term here because it's equal to 1 and that doesn't change anything. So velocity squared is 625 taken from here, divided by gravity 9.8. That is equal to 6.38 meters. And that's how from just a single velocity vector we found the optimal angle and the horizontal distance covered when launched at this optimal angle. I'll now give you the chance to pause and try this problem on your own before I go through the solution. And now I'll solve it. So we have a projectile launched at 22 meters per second and the angle is 40 degrees. How long does it take to return to the same height it was launched from? This is different wording to normal, but what that means is simply when does it hit the floor? Because it's launched from the floor and then it hits the floor. And it doesn't have to be a floor that's arbitrary. It's the same height, and that's what matters. Since we're looking at air time, the horizontal speed actually does not affect air time. This is what Galileo discovered. No matter if your object drops straight down or it has a horizontal component of velocity, it hits the floor at the same time under the same acceleration. And the acceleration being gravity. That is 9.8 meters per second squared acceleration. So that means all we care about is the vertical velocity component. In this case, this vertical velocity component is 22 sine 40. Take it from here and here. That is equal to roughly 14.1 meters per second. Now, to find the time it takes to reach the bottom, there's a special trick we can use. We can find the time it takes to reach the peak and then double it because it's a symmetrical launch with equal trajectory on both sides. The time it takes to reach the peak can be found with this formula because it involves all the variables that we know. Velocity equals y component of velocity minus gravity time. And what's special about the peak, aka the turning point, is for a very brief moment when you're changing direction, velocity crosses 0. So for the brief moment that velocity is 0, that's what we're solving for. Velocity equals 0. The initial launch y component was 14.1 minus 9.8 time. If you rearrange for time, you'll find that time equals 1.44 seconds. That's to reach the halfway point, the top. Then we just have to double it, which is 2.88 seconds. That's the answer to the problem. So that's how Fluent students approach projectile motion. If you see someone doing it without guessing or freezing, this is the kind of thing going on in their head. And if you want to learn this structure for every physics topic, regardless of your IQ, regardless of your past, and regardless of your knowledge level, and actually train your brain to solve things instead of just memorize formulas, the Physics Fluency Challenge is where that starts. I built this for students who want this to finally click.